In this lecture we look at decision trees. Decision trees are actually graphs, or special graphs that are called trees, and decisions occur at the vertices of the trees. So in some sense this will be the first time we look at network models in which there's something actually happening at the vertices themselves. To begin with, though, we're going to look at dependence and conditions. We've looked at independence, but we're going to look at dependence and conditions where a condition can be either true or false. Let's review. Last time we looked at a sample space and that we can associate a random variable with a sample space. We have notation, the probability that x is O sub j is the probability that outcome O sub j occurs. Sometimes we simply write P sub j or P of j. And very often we use x instead of j and write P sub x or P of x. And little x is a value and big X is the actual variable. Information, we saw, is measured in units of bits defined by a logarithm on a probability. And entropy is the expected self-information or the average information, and is given by this summation. Joint probability, we saw, is essentially the same idea. The sample space has two indices for each outcome. We have two variables, a capital X and a capital Y, and it can take two different collections of values, small x and small y. Marginal probabilities are probabilities of the x and the y respectively. And joint information is, once again, a negative logarithm base 2 of probability. We also had joint entropy, and joint entropy is defined as just the sum over the joint probability distribution of the joint information, and therefore it's once again given like this. Now later on we're going to show that the joint entropy is less than the sum of the individual entropies, but for right now we're just going to be using the two independence ideas. If x and y are independent variables, then self-information of individual outcomes is the sum of the self-informations, and entropies, or average information, is the sum of the averages. And remember, I here measures individual outcomes, whereas H is averages over all outcomes. You can show pretty quickly that if x and y are independent, just using properties of logarithms, then the joint probability of x and y is just the product of the individual probabilities. Well, what if x and y are dependent? In particular, if x and y are dependent, what can that tell us about the likelihood, or what can knowledge of one tell us about the likelihood of the other? We're going to look at an idea called conditional self-information. So suppose x and y are variables associated with a random process, and suppose we have a condition on a variable x, which is a statement that involves x that's either true or false. For example, we might have, is capital X, the variable, equal to some value, little x, or some possible outcome. So if we have a condition, then the information we get from capital Y taking on a value little y, given that condition, is the self-information or surprisal from y equals y occurring, given that this condition is known to be true. So how surprised we are knowing the condition that the little y actually occurred as a value of y. Conditions are often of the form is capital X equal to little x. And often we write conditional information in the form I of y equals little y, given the condition that x equals little x. The bar there just means little x. Bar there means given that. And very often we just drop the capital X's and Y's and write the self-information of y given x, and this is capital Y taking the value little y, given that capital X takes the value little x. as we see here. Intuitively, the self-information of y given x measures how surprised we are that y took the value little y given that x equals x. We've seen all this before. For example, if x is my coin and y is U's coin, then independence can be thought of as things that are happening completely independent of each other on opposite sides of the earth, for instance. So if I have independence, then the self-information from y given x, it's just the information from y itself, because regardless of whether or not I got heads or tails on my side of the earth, U is going to get his outcome completely independent of that. So the condition x doesn't increase or decrease the information. But dependence is a different story. Suppose you and I are in the same place with our coins attached to opposite ends of a ruler. So if I got heads, it's no surprise whatsoever that you got heads, and therefore the self-information is 0. In other words, the information from y given the condition that capital X is little x is simply the information from the joint information I of xy beyond what we already had from I of x already. In other words, we can simply write that the conditional information is the difference between the joint minus the information just from x itself. So for example, if x and y are independent, then the information from y given x is just the joint minus I of x, but the joint, because they're independent, is the sum of the individuals, and that's I of x plus I of y minus I of x, and that's just I of y. So what we're saying there is that if we have independence, then the information gain, or the information difference, is exactly the same as the information generated by you, independent of me. On the other hand, if I of xy, if the joint probability, the joint information is the same as the information for just a single variable, like it would be if my coin and U's coin were attached to opposite ends of the ruler, the difference would be 0, which is given by this. So total dependence of y on x means there's no new information from y once we know x. Let's look at some examples. Suppose Jane chooses from 3 cards numbered 0, 1, and 2. Let's suppose John chooses a card from the 2 remaining. So x will be Jane's card and y is John's card. We've already looked at this example. We know that's the sample space, and we know that this is the probabilities. Therefore, the informations are all the log base 2 of 6. We also know that each of the 3 cards is equally likely, so the information is the log base 2 of 3, 3 being the m here. So what do we have? We have the joint information is the log base 2 of 6, and the information for x itself is the log base 2 of 3. And this is the information for all possible values of x and y, because y is not allowed to equal x the way these are chosen. And now we look at the conditional information of y given x. That's the difference of the joint minus the individual, log base 2 of 6 minus log base 2 of 3, log base 2 of 6 over 3, and that's 1. In other words, the joint information is 1 bit, which means once the value of x is known, in other words, once Jane's chosen a card, and we know what it is, the outcome for y can be encoded into a 1-bit string. Conditional probability is the likelihood that y is equal to y given x equals x, denoted with the bar again. And we tend to think of the conditional probability as the likelihood that y takes on a certain value, given that we must have something occurring with X. And a lot of times we're shown this formula, and this formula makes sense in that the largest possible value of Pxy is P of X, so therefore the conditional probability has the largest possible value of 1, so it is truly a probability. But let's prove this formula using self-information. To do so, we use the definition of self-information in terms of the base 2 logarithm, and we use this idea of self-information, conditional self-information, being the difference of the joint minus the individual. So we substitute in the logarithms for the informations into this nice result we have about the conditional being the joint minus the individual. And then we have some algebra to do. We'll cancel the logarithms. But remember, the difference of a log is the log of a ratio, of a fraction. And from that we end up with our formula. So let's look at an example again. This was our sample space. Probabilities are a sixth. The individual probabilities are a third. So the conditional probability is a sixth over a third, which is a half. And the conditional self-information is once again 1 bit, which means 1 bit to encode the outcome for John once we know what card Jane has selected. So specific conditional entropy is entropy of a variable y, specific, or that occurs when a given condition x equals j is implied. And it's simply defined in terms, once again, of the bar, where x is known to be the value j. So the specific conditional entropy is the average information of the variable y given the specific outcome x equals j. And it's a measure of the information in y. So it doesn't say anything about j or x because we already know what they are. In terms of x equals little x, we can write the specific entropy in this form. We define the information gain to be the difference of the entropy in y minus the entropy in y given x. And we can think of this as a change in entropy from a prior state. So beforehand there were no conditions. Afterwards we know that x equals x, and the information gain is the information we obtain going from the before to the after. Alternately, we can think of the information gain as the uncertainty lost, because uncertainty is another interpretation of entropy, and information gained tends to mean uncertainty reduced. So information gain is defined by specific entropy. So in general, we could write a just condition sub x, and that would be the entropy specific to the condition x. And then in general, the information gain is y given the condition is equal to the difference of the entropy in y minus the entropy in y given the condition. So in summary, anytime we say conditional, we're referring to the fact that if y depends on x, then information from y may be reduced by the knowledge that x equals x is certain to occur, or uncertainty may be reduced. In general, information theory says that these kinds of reductions are due to differences. Differences in joint minus the individual, or differences in the individual entropy minus the entropy given a condition x.